Hi, my name is Jan Wilczek and I am the founder of the Wolfsound blog and YouTube channel on learning audio programming. One of the most important tools for audio programmers creating cross-platform audio plugins or desktop and mobile applications is the JUCE C++ framework. It is my privilege to share with you that the JUCE 8 preview branch has just been published. The JUCE team, together with an external developer, have been working really hard to act on the feedback from the community. From countless discussions at conferences, on the JUCE forum and through email, they came up with a list of features that have made it into the release. And the main new features of JUCE 8 are WebView-based graphical user interfaces, completely new animation framework, vastly improved Unicode support, direct 2D renderer integration on Windows, new JavaScript interpreter engine. Other changes with JUCE 8 include new end-user license agreement, which is clearer and more understandable, and a new pricing model. More on these at the end of the video. If you're eager to check out the new features, you can do so by going to github.com/juice-framework/juice and looking through the preview branch JUCE 8. You can clone it locally, run the demos of the new features, and already start integrating them into your projects. In this video, we will go over all these features so that you have a reference point of what to expect and how to get started. We'll not delve into fine-grained details, but we'll discuss enough to give you a good feeling about each particular feature. We'll conclude with the explanation of the exciting changes to the license agreement and the pricing model, which is something you don't want to miss out on. Let's start with probably the most thrilling feature of JUCE 8, the WebView-based graphical user interfaces. In recent years, there has been a lot of interest in cross-platform application development using web technologies. You may know it from web apps and progressive web apps. You may know it from hybrid apps that run a browser inside the desktop application window. To facilitate this shift in the industry and to satisfy the market demand, JUCE 8 introduces WebViews to your UI creation toolbox. What do you get? You can write the GUI of your plugin or audio app in any web front-end technology that you like, be it React, Angular, HTMX, or even classic plain HTML, CSS, JavaScript combination. Imagine what would be possible if you could outsource creating the front end of your audio plugin not to a JUCE developer, but to a front-end web developer, while you focus on the audio processing part or business logic of your application. Here you can see a somewhat traditional example of a GAIN plugin. This is not a mockup, this is an actual plugin that can be run in a digital audio workstation. The coolest thing, apart from the fact that the GUI is written in a web front-end technology, is that the GUI can be developed and tested completely offline using a browser of your choice. Now, when I saw it for the first time, my immediate question was, okay, but how does it work? Under the hood, JUCE uses a WebView rendering engine which is native to the given operating system. It is WebKit on macOS, Microsoft Edge WebView 2 on Windows, which is based on Chromium, and GTK WebKit 2 on Linux. This approach is different from the one used in Electron Framework or Chromium Embedded Framework. Instead of bundling an entire browser into your JUCE-based software, JUCE leverages technologies already available on your end users' devices. There is no need to bloat the installer with huge dependencies. At the same time, you get the best performance possible thanks to the native integration. You, As an application or plugin developer, create an instance of the web browser component class that has already been present in the previous releases of JUCE. However, now, instead of directing the instance to an arbitrary address on the web, you can intercept URL navigation and provide your own web-based content for the component to render. This happens without the need to run a local development server, although, of course, you can run one if you like. But that's not all. From C++, you can provide any resource that the website requests, including text data, JSON, CSS files, audio, basically any MIME type. Your C++ code is the backend. Now, what about controls like sliders, buttons, or combo boxes? How can these communicate with the C++ backend? Do we still get the benefits of using the parameter class, for example, with the audio processor value tree state? Yes, we do. New classes have been introduced to do exactly that. You have a web slider parameter attachment, a web toggle button parameter attachment, and a web combo box parameter attachment. You can also use exactly the same slider listener interface as before. To facilitate communication with native web elements, a set of classes has been introduced. These classes relay user actions and automation back and forth between your C++ parameters and their visual representation. They are called relays. Now comes the question: what is actually possible in terms of WebViews and C++ backend integration? On the C++ side, you can execute JavaScript code in the context of the WebView document. This gives you a chance to interact with the document object model, the DOM, similarly as you would directly in JavaScript. You can also listen to events emitted in the WebView, evaluate custom JavaScript code in the WebView before any resources are loaded, and provide a set of key value pairs that will be accessible from JavaScript inside the WebView. On the JavaScript side, you can listen for events emitted from the C++ backend, call a registered C++ backend function asynchronously, and retrieve an online resource or a resource provided by the C++ backend. This set of features should be more than enough to facilitate even very sophisticated integration schemes. Another question you might have is on the performance of the web-based GUIs. JUCE does not reinvent the wheel here. It takes advantage of the state-of-the-art tools native to each operating system your app or plugin runs on. Since WebView rendering engines are developed by the operating systems providers, your WebViews benefit from their support. If current trends continue, web-based front-end technologies in desktop applications will be more and more widespread. The rendering engines themselves are evolving at a rapid pace too. Therefore, the CPU load will be on par with that of web browsers, which are highly optimized. As usual, resource consumption will depend on the content of the rendered user interfaces. It's up to you how to implement, structure, and benchmark them for optimal performance. If you're worried about the performance of the front-end and back-end communication, you will be happy to hear that it has been tested thoroughly. Even with thousands of parameters with ultra-long identifiers, the test plugin remained responsive. Finally, I do not want to overstate this, but it seems that with the introduction of WebViews, plugin and app creators get an almost limitless range of possibilities. For example, with this feature, you gain instant access to cross-platform hardware-accelerated graphics via WebGL. If you want to see for yourself how to integrate a React-based frontend with an audio plugin, check out the WebView plugin demo provided on the JUCE 8 preview branch. I am incredibly excited to see what new and innovative plugin and app interfaces you will come up with using front-end web technologies. The introduction of WebViews does not mean the JUCE team has abandoned C++-based graphical user interfaces. On the contrary, JUCE 8 includes a huge number of features and improvements exactly in that regard. So let us move to another exciting feature of JUCE 8, the brand new animation framework. Up to this point, animations in JUCE were rather cumbersome. You had to inherit from the timer class to be able to implement the timer callback, where you needed to kind of manually update the position of your components. If you specified the update rate in code, you were likely to be doing too few or too many updates per second, which would either cause your animation to be janky or too CPU consuming. Since JUCE 7.0.3, you could synchronize the timer callback with the refresh rate of your screen using the vBlank attachment class. However, it was still quite cumbersome to track the positioning of each animated component. JUCE's component animator allowed only basic linear change in animated components' position or alpha level. Specifying custom animation curves was left to the user. However, as of 2024, many front-end frameworks supply easy-to-use APIs to allow custom animations with high-level concepts. The completely new module, JUCE Animation, in JUCE 8 addresses this issue. You can now animate any parameter of any of your components or a group of components using simple-to-create animation speed curves, so-called easings. All animations can be synchronized with the screen refresh rate and do not make your layout code polluted with handwritten animation curve calculation code. How does it work? The whole concept revolves around animator class instances. An animator animates a certain value along a specified easing. You can hook into the start of this progress each update that occurred and also its end. In these callback functions, you can update the parameter of your component you want to animate and order the component to repaint itself so that the changes are visible on the screen. Animator class instances can be easily created using the Value Animator Builder class, which allows you to easily chain specifying options of your animator. In the builder, you can specify what the easing should look like. An easing is in fact a function that maps a float value to another float value. You can think of it as a mapping that bends the linear change from the origin to the desired value. Of course, you don't have to write one manually. JUCE provides a set of predefined and customizable easings for you. You can easily create any easing you may know from the CSS domain. Let's look at a short example. Here you can see an application's UI. Let's imagine I want to display a short message that should stay on the screen for a moment, a so-called toast. You could make the toast appear instantly in place by explicitly drawing the toast upon request. That, however, does not feel very modern and may be perceived as too rapid by the user. You could make the toast smoothly land in its place and then fade out. This can be implemented by controlling the position and the alpha level of the element from the timer callback. However, any more sophisticated transition that is non-linear would be cumbersome to implement with the existing APIs. With the new animation framework, it's trivial to create a modern-looking slide-in animation and a fade-out for a toast. As you can see, the position and fade-out change non-linearly. How to implement an animation in your own audio plugin or application using JUCE? 1. Decide which parameters of your component subclass you want to animate. Is it the position of a particular element? Is it its opacity? Is it its color? Whatever it is, be sure to encapsulate it in a field that you can easily update from an animator's update callback. 2. Build the animator instance using a Value Animator Builder. Here we can provide a callback that will be called once the animation starts. A callback that will be called at regular intervals, where you can update the animated parameters of your component and repaint it. A callback that will be called once the animation completes, the duration of the animation, the easing of the animation, whether the animation should run infinitely, and a custom callback creator if you want to have different parameter update routines depending on the current UI state. 3. Create a vBlank animator updater instance as a member of your custom component. 4. Provide the created animator to a vBlank animator updater instance so that it gets updated at screen refresh rate. 5. Start the animation by calling start on the animator instance. Do you want to build complex animations with various transitions and multiple things happening in sequence or in parallel? You can build an entire animation execution graph using an animator set builder. It allows you to chain animator instances, delays, and plain function calls with a very intuitive API. One important note though, your animator instance must not outlive the thing it animates. If you animate a component subclass instance with it, you can simply place the animator instance as a member of the component subclass. Object lifetime management is bread and butter for C++ programmers, so you should have no problem setting it up. JUCE 8 also comes with improved Unicode support. Unicode is a standard designed to consistently encode, represent, and handle text expressed in most of the world's writing systems. JUCE 8 contains a whole set of improvements in this regard, so let's go over them one by one. The most important change for developers already using JUCE is the added support for reading the correct and same font metrics on all platforms, while still maintaining the ability to use the font metrics used in older versions of JUCE for backwards compatibility. To understand the importance of this, we need to define the difference between a typeface and a font. Most simply, a typeface, also called a font family, is a set of fonts. For example, Verdana is a typeface. A font is a very specific set of glyphs with fixed properties like weight, size, and style. For example, Verdana, bold, size 12, upright is a font. In this context, consistent typeface metrics across platforms in JUCE 8 ensure that the font you selected looks exactly the same on all platforms supported by JUCE, even if the operating systems report different metrics for a given font. That also includes mobile platforms like Android or iOS. For example, the legacy metric system of JUCE 7 resulted in slightly larger text on Android. Now, the provided metrics will result in consistent user interfaces across all supported platforms, thus alleviating the need for a lot of fine-tuning. At the same time, if you have already invested a significant amount of time into making sure that your text looks great already on all platforms, you have the option to preserve the legacy typeface metrics. A lot of effort and testing was also put into backwards compatibility for glyph positioning so that the positioning with new metrics is as close as possible to the positioning with the old metrics. To facilitate metrics-related changes, old font class constructors were deprecated. New code should use the constructor taking font options as its single argument. A cool addition to fonts that will definitely be valued by a lot of users is the support for emojis. Now you can embed them into text and enjoy their presence in user interfaces. Although not all conceivable emojis are supported because of the richness of the emoji ecosystem, you will most likely find what you're looking for. JUCE 8 also added support for fallback fonts. It means that you can render emojis or multilingual text and not worry that the glyphs won't be rendered on the UI. If, however, you need more fine-grained control, you can override the fallback mechanism and specify the fallback fonts yourself. For example, if you want to bundle your own emoji font with your plugin or app. As usual in JUCE, you can just go with the defaults, but if you want the fine-grained control, you have an option to do it too. The JUCE team has also changed the way that typeface lookup works a little bit. If you've created typefaces with the create system typeface for function, then looking up a font by name with a given style will search through any typefaces currently loaded from memory before going to the operating system, which avoids unnecessary OS calls. Let's now move to another feature of JUCE 8, direct 2D support. All JUCE components, all the windows, dialogues, and widgets you see in JUCE applications are rendered using a renderer. Before JUCE 7, only 2 renderers were available on Windows, the software renderer, which was the default, and the OpenGL renderer. On macOS and iOS, the core graphics renderer was used by default. In JUCE 7, the core graphics renderer was dramatically improved on macOS and iOS. Since the core graphics renderer is based on these platforms' APIs, it can leverage all their capabilities for optimal performance and high-quality rendering. Now, in JUCE 8, developers for the Windows platform get a similar native support. Starting with JUCE 8, the direct 2D renderer will become the default on Windows. However, you can always change the renderer of a component and its children through getting the peer component with the component getPeer function, and then using the component peer setCurrentRenderingEngine function. If you want to see the new renderer in action and compare its performance to other renderers, you can build and launch JUCE's demo runner on Windows. There, in the GUI section, there is a graphics demo where you can see how long does rendering of a single frame of a complex animation take and what its effective frames per second rate is. On my machine, the speedup can be almost tenfold at times. The capability to use direct 2D features in your plugin or app UIs allows hardware acceleration and high-quality rendering, for example, sub-pixel rendering or anti-aliasing for smooth edges. The new renderer can cache paths and images in the GPU for better performance and perform sub-pixel positioning of the components. Additionally, since it's a Windows native technology, the direct 2D renderer should have a broader support among devices running Windows than the OpenGL renderer. The final JUCE 8 improvement that we'll discuss in this video is a better JavaScript interpreter. I don't know if you're aware, but JUCE has the capability to parse and execute strings of JavaScript code. This has been possible thanks to a custom JavaScript engine embedded in JUCE. However, now, the JUCE team has replaced this custom engine with Quick.js. The new interpreter is not only faster, but also allows you to run any ES 2023 compliant JavaScript bits in your app or plugin. That was it for the technical features of JUCE 8. That's not, however, the end of changes introduced in this release. With JUCE 8, there are significant changes to the end-user license agreement. Above all, it has become more readable. You should be able to easily understand it without the need to contact a lawyer. As an important part of pricing changes, you have been granted a very generous personal license. Creating personal or non-commercial software with JUCE 8 is free and has all features of the paid license. For example, that means you won't see the annoying splash screen each time you launch your personal app or plugin. And all that regardless of your personal income level. Finally, it's important to state that the new license agreement is different from the one present in JUCE 7. That's why it's important that you read it before deciding to use JUCE 8. Thanks to the clear wording, you should have no problem understanding it in full. These were all the major features and changes introduced in JUCE 8. What do you think of it? Which features are you planning to use in your app or plugin? Let everyone know in the comments below. Once again, if you want to try out the new features, You can do so by going to github.com/juice-framework/juice and checking out the JUCE 8 branch locally. Don't forget to visit juice.com for further details and enjoy creating cross-platform audio apps and plugins with the JUCE C++ framework.